Dr. Krishnakumar Menon, that is from Nano Science at the Andhra Institute of Medical Science, Kochi. Then we have Dr. Suresh Kumar, again from Kerala Veterinary and Animal Science University, and also Professor VPN Nampoori, sir, very eminent professor in physics, especially botany, and he was in fact appreciating the work of modern framework. And so these are the two people, and then to speak with, we have our Professor KM to speak on vision. And one on electron neurophysiology also we will continue. So when you make both of them to do that. Then we have Alan Lobo. Then some people are joining online also. Anyway, after the lecture, we will introduce them and we will proceed. So I request Professor Krishnakumar sir and Professor Nampoori sir to conduct the session.
Before Professor Krishnakumar sir takes up, who took the time out, listened and made so many things ready for this event. So I envy his students, because the temperament, the open-minded temperament that he shows is really good. So, sir, thank you so much for supporting this event. And please, sir, as you chat. Thank you.
And it's excellent that Alan Ecology Department said that this is an interesting person, you should be with him. And he is very much into the right. He always talk about glycolysis and everything. You should meet him. So he just walked in, whistling through the corridor, that I remember very well. And just to have a casual talk only, but apparently he ended up giving a seminar in front of us. And we got all our students, and that's the way the entire thing began. At the outset, the other thing which I wanted to tell is that particularly in relation to this topic, we all know that phosphorylation, oxidative phosphorylation happens in the mitochondria, but actually, you can show that just in presence of reactive oxygen species, you can have the ADP formation in presence of ADP and the inorganic phosphate. So you don't really seem to require a proton pump, etc. So what does this mean, really speaking? And you look at all the other enzymology aspect. When you look at everything works on the basis of electron oxidative reaction. Say, for example, in an enzyme active site, what happens? In the active site, what is it doing, really speaking? You say that the substrate is binding and then the product is formed. But actually what is happening is a rearrangement of the electronic configuration in a very subtle way, or a microsurgery being, and this is the key thing, how this is being facilitated. So in other words, it's not just the enzyme alone is responsible for all these things. The entire structural complexity of the enzyme is maintained by all these different reactive oxygen species, which can bind to different regions of the enzyme. You look at, you simply do a docking study with everything with a different binding energy. So in a similar way, all these things can happen to everything. So in other words, a chaos being beautifully organized in the system. So this is where the Merban concept comes in a big way and facilitate the entire thought process, what has been generated over years by different scientific endeavors. So with this note, I would like to
Alan Lobo. I have been talking a lot. I think he's a young, wonderful. I'll introduce him.
It's a joy to introduce Alan Lobo, Dr. Alan Lobo. He came into my life through my student Danny, who is a colleague of Alan at St. Joseph's University in Bangalore. He said, here is a guy who wants to be associated with us and wants to work on woodworm. So Alan has been an ardent physicist and he is into computational biophysics. He did his master's from Madhya Pradesh and PhD from Krishnakumar University. He is independently motivated. We took this project of, I don't know how many of you have heard the molecule kinesin. How many of you have heard kinesin? Anybody here? Kinesin? Nobody. It's, Alan, do you have a video on kinesin? Yes. Wonderful. So he will take you through, and I challenged him that in the next 1.5 months, let's see if we can solve the problem. So he seems to have a solution. Let's see what it is, and let's see where he takes us. The floor is yours, Alan.
Thank you. Murban concept in a slightly different way, okay? Stepping out of the influences of diffusive reactive species, we try to explore the electrostatics which governs the entire mechanism, in which not just your diffusive reactive species, but also how protein complexes and membrane complexes they interact with each other. Alright, so that's what the title is, protein electrostatics and stochasticity. Alright, so what is the idea? Now when you explore the biochemistry, in which we realize that there are some complex proteins which kind of behave as mechanical machines in a very engineered sense. They have certain functionalities which are very peculiar, and they move, or they are engineered in such a way that they have a very high predictability and a very high, you can say, intelligence, and they start functioning along that intelligence. Now normally when we talk through physics point of view, such an intelligent engineered architecture is usually not the case at such micro scales. Alright, there is something in physics which I think all the students will be very fresh with, something called principle of least action, which basically dictates that if nature has a way in which the energy requirement is lesser, nature will always use that approach as the most desired approach. That's called principle of least action. It's a very canonical principle. Canonical in the sense, a very holy principle in physics. Now, so where does Murban concept stand there? So Murban concept essentially challenges the intelligence aspect of these mechanical protein motors. Alright, we take the example of a system in which there is a field, some force field which is happening, a very general force field, and along with that there are these diffusible charged species, what Murban concept refers to as DRS. So they are basically charged species which are suspended in a bath, in a matrix in which they can move. And keep in mind, this matrix at that intracellular scale is a very viscous medium. Alright, at that level it would be like trying to swim through a concrete liquid, a concrete liquid. So the Reynolds number, for those of you who value the numbers, the Reynolds number is approximately 10 to the power minus 12. So it's very viscous medium. So now if you combine these three phenomena, a field, some type of force field which is present there due to the electrostatics of the surroundings, some diffusible charged species, and a bath of mobile ions. So the system, or you can say the body, would start moving in such a fashion. This is one simple simulation which I have made in MATLAB to demonstrate what happens when a body tries to move in such a medium. Alright? So what is this electromotor physiology that we are trying to talk about? The general principle, when we take the example of this protein, I'll talk about kinesin a little later. The idea is that there would be a combination of these three physical quantities: a field, the presence of diffusible reactive species, and a thermal bath, a matrix. And when these three combine together, we see phenomena occurring in a much more relaxed or passive way rather than an engineered approach. So that is the idea, that's the entire hypothesis with which we move. So we start with the understanding of this kinesin protein. Alright, so kinesin is a very well-known, or you can say a very well-regarded discovery which was done in 1985 by Ronald Wayne, and he even won the Shaw Prize. For this discovery. Alright, this protein is known for transporting materials by literally walking over the tubulin, which you will see in this video here, this short video here, you will see how this moves. Okay, we'll look at this video a little later as well. All right, I've shared the YouTube link here. All right, the structure of this protein you can see somewhat here. You can see these 2 feet are there. Okay, these 2 feet are there, and you can see this is the prototubulin. All right, the microtubule basically, which is composed of this alpha beta tubulin proteins. All right, you can see a lot of work has been conducted in this regard. All right, this is a well-known problem called the kinesin problem. If you just Google what is kinesin problem, this problem pops up. All right, what is the problem? The problem is how does it move the way it does, and why does it move the way it does? All right, you will see ever since its conception in 1982, where it was hypothesized that there must be some protein which is transporting materials across this microtubule, and its discovery in 1985. A lot of work has continuously been going on to discover different types of proteins in the kinesin family and to try and figure out the structure, the mechanism in which it moves, or the structural dynamics in which it moves. That's the most recent topic in this field of kinesin proteins that is going on. Alright, so the question is not whether it moves or not. We know, we have experimental evidence also that it actually moves, but the question is how does it move the way it does and why does it move the way it does? Alright, that's the point of focus. Now, what is the classical story behind it? The classical story is that an ATP docks to one of the feet, which is actually called the kinesin motor domain here. These 2 feet you can see here. The literature refers to these 2 feet as kinesin motor domain. So that is what we will call it throughout the presentation. So the classical idea is that ATP binds to this feet and somehow gives it an energy to jump by a very well-defined distance of 8 nanometers and then move to the next step. Alright, because of this, this is how the motion actually looks like. So if you look at the 2 feet here, you will realize it's a very structured, very engineered type of motion. Alright, and this is the classical idea behind this. Okay, this is the classical explanation behind this. But this classical explanation brings with it a lot of questions. First question is, how does the protein know? How do the two kinetic feet know exactly where to step and how to step? And how do they know of this exact 8 nanometer step? Alright, how do they know of the gait, the pattern in which they are walking? The pattern that is visible in this video is called hand over hand pattern. Alright, in which they are actually, walking, like we humans do. So how does the system know? And second thing, as I told you, the system is actually a very viscous medium. So systems cannot just walk very freely as is represented in this animation. In reality, you require a strong force for the protein to move, for the complex to move here. So where does this force come from? Is ATP alone sufficient? When we look at the experimental evidences, we realize that some numbers do not match. So now let's take a look at what is the experimental observations. First of all, as I told you, each step is 8 nanometers, exact 8 nanometers, alright, which is a very well-defined value. We have seen this in cryogenic photographies. And also, the maximum speed with which it can move is 800 nanometers per second, alright, and it can move a maximum of 1 micrometer in one run when it is unloaded. That is when the kinesin is unloaded. If you look at this big vesicle here, this is the load inside which the stuff is being carried. Now, what are the problems with the existing literature? There are a lot of problems actually. Alright, the possible explanations. First of all, there is no explanation of why it moves the way it does. Second, there is a lot of confusion of the pattern and the symmetry in which it moves. Alright, you can say the hand over hand fashion, or there is an asymmetric walk. Sometimes there is an inchworm fashion in which one hand, or you can say one feet, moves more than the other feet. So there are a lot of questions regarding this. One major problem is the presence of intelligence. So how does this protein complex know about the exact values? Alright, this 8 nanometer step and stuff like that. Alright, so what is the hypothesis derived from the Mulban concept? Of course, Mulban concept tries to challenge this molecular intelligence idea. Alright, so as I told you, Mulban concept, apart from the actions of DRS species, diffusive reactive species, it also has another, you can say, a more global outcome. this concept. The outcome is stochasticity plus the interaction of diffusive charge species. Now, the moment you say charge species, you realize you're dealing with electrostatics. Alright? And the moment you say electrostatics, coupled with stochasticity. So, stochasticity is actually a very important term here, okay? It means motion of bodies under the influence of some random noise. Alright, so what does it actually look like? You see the simulation here. You see this, the blue particles are the particles which are the matrix. They are continuously colliding with this red particle here, and under that influence, this red particle is moving randomly. This is called Brownian motion. This is the most fundamental example of a stochastic model. Alright, so this type of a behavior coupled with electrostatics is what Morvan concept actually presents in terms of physics. So when you couple these two together, you actually create a new, you can say, field of study in physics, soft matter physics, as a matter of fact, electrostochastic thermodynamics. Alright, and we have models, we have mathematical models which kind of explain such systems. Alright, so as the very beginning of our work, what we try to do is we try to create a mathematical model to replicate a system moving in a media with the same parameters as our cellular matrix. Alright, we chose the Reynolds number as 10 power minus 12, which is an experimental value. We chose the temperature to be 300 Kelvin. Alright, the unit of energy is 1 kBT, where kB is the Boltzmann constant, stuff like that. So the equation and all this is the Langevin equation. We will not go into too much detail of the equation. The results are what is very interesting. Alright, so what are the results here? I will tell you. First of all, there are experimental data which tells that to move at that distance, to move at that scale, the protein requires an energy value of somewhere between 12 to 16 kBT. Alright, 12 to 16 kBT. To put in perspective, 1 electron volt is equivalent to 11,600 kBT. Alright, so that is a scale that you can refer to. Now, when we do not use this idea of a power stroke, that is the ATP giving some sort of a spring to the feet and jumping from one point to the other, we are still able to calculate this energy value very precisely, that is 13.5 kBT. That is, if we just allow the system to move by itself in this media, we still see that the energy requirement is the same. Also, what is interesting is that the force that was required, the experimental evidence says that the stall force of 6 to 8 piconewton is required, and we get the calculation to somewhere about 7 piconewton. Alright, and also the maximum speed with which the particle can move, the system can move in this type of media is 800 nanometers per second, which is also the experimentally derived value. What this means now, you can see a lot of resemblance here. It does not conclusively prove that maybe the stochastic model is correct, but it also points us to the right direction. At the very least, it points us to the right direction. What it also does is that it shows that the hydrolysis of ATP, which is what is responsible for, in the classical model, to cause this feed to move at that distance, is the energy equivalent of 1 ATP hydrolysis is 1 kBT. Alright, 1 kBT, which is mentioned here. However, in order to move by that distance, the minimum energy required is about 20 kBT. So there is a huge mismatch in these values. So now the question is not only whether ATP is responsible for it to move or not, but the main question is, where is this extra energy coming from? Alright, so now we go back to the Morvan idea. We try to find if there is any electrostatic interaction between the kinesin feet and the tubulin on which it works. So we do a lot of studies on the protein structures of the concerned systems here. So this here is an alpha beta tubulin, alright, which is the structural unit of one protofilament that is in the microtubule. And what we do, we create a path using this alpha beta tubulin like a cylinder. You can see this cross section. Now the idea is that the kinesin starts to walk on top of the cylinder. Right, the kinesin will walk on top of the cylinder. If you look at the video, if you see that video once again, you will realize that this kinesin is actually, you can see this kinesin is walking on top of it. So each structure here, each structural component is this alpha beta tubulin. Alright, so we are going to analyze the feet and we are going to analyze the path on which it works. So what I do is using this workflow, alright, I take the PDB, I clean it in Chimera X, and then I convert the PDB to PQR, that is the coordinate file set of all the atoms in the protein complex, and I pass it through APBS, which is basically a Poisson-Boltzmann solver, which gives me the potential, electrostatic potential landscape. Alright, when that happens, what you see here is that the electric field and potential of the region around this alpha-beta tubulin is in this graph, the electric field and the electric potential. Above is the electric potential, below is the electric field. Alright, now this alone does not make a lot of sense here, okay, because there is not just one dimer on which it works. So what I do now, this is the actual protofilament, as you can see here, the actual cross section of microtubule. The PDB ID is 5SYF. It's taken from RCSB. Now I take two sections here, one as you can see along the surface of the microtubule and the other along the axis of the microtubule. Alright, now it is known that as you can see here, the kinesin will walk on this surface here, as you can see. I analyze the electric potential and electric field, electrostatic potential, electrostatic field around this protofilament. Or when I do that, I realize something. You see a lot of periodicity here. Alright, when you look at colors, as it becomes red, it is more positively charged, as it becomes blue, it is more negatively charged. You see a lot of periodicity. Alright, that periodicity dictates something. It means that the potential field is actually repeating itself. Alright, so you can see that same thing here. So this is just a cylindrical version of the same protofilament here. Alright, you see a lot of periodicity. What is very interesting is that the distance between one high and one low, that is one peak positive potential and one negative potential, is exactly 41 angstrom, which is 4.1 nanometer, which means the distance between every two positive potentials is exactly 8.2 nanometers. Alright, which is very much in lines with the step size of this kinesin heads. Now I look at the three heads here. Alright, the kinesin motor domains, kinesin feet here. So we have the apostate. Apostate is the state where nothing is attached to the feet, and we have the ADP attached feet and the ATP attached feet, ATP-like attached feet here. And what I do is now I know that the protofilament on which this feet, this kinesin is walking, is actually a charged system. It's a landscape. It's a landscape of electrostatic potential. So now what interacts with a charged field? A charged body, right? So if my hypothesis is correct, the three heads should be charged, should have some charge, and they do, as a matter of fact. Alright, so this is the potential of the charged landscape of the kinesin feet in the ADP state, ATP-like state, and the apostate. Alright, so you see here, it's not just that they are charged, you see the local concentrations of positive charges and negative charges in certain regions, which means the feet, they actually behave like dipoles. So now what I do is I take this feet and I just carry it and move it along the protofilament, just to see how this feet interacts with the potential of the protofilament here. When I do that, I realize something very interesting. When you look at this graph, you see that when ADP is attached to the feet, this blue line here, it is rather free as compared to the apo and the ATP state. What it means in biochemistry, it's basically when you have this protofilament and you have the feet of the kinesin, if the kinesin feet has ATP attached to it or nothing attached to it, in either case it is very nicely fixed on the protofilament. But the moment ATP hydrolyzes to ADP, it becomes loose. You see this energy gap here, the y-axis is energy gap. You can see a huge and a kind of a constant energy gap here. So you see, because of this, because of the ATP hydrolysis, ATP becoming to ADP, that is, the feet becomes loose. Alright? So once the feet becomes loose, there must be some force which causes it to move in either way. Alright, so we'll see that as well. So after this analysis, what we do is we perform a steered molecular dynamics of this entire study. And when we do that, we again realize something very interesting here. As shown, now this is actual data. This is not a mathematical model, but this is actual molecular dynamics being run on the cryo-EM structures of the protein heads and the protofilament. What we see is ATP, the blue dots and the black dots are ATP and apo states respectively, and the red one is the ATP state. So what is happening here is when you take this protofilament and the kinesin feed with apo state or ATP state, it is very closely attached, as I told previously. When this ATP hydrolyzes to ADP, what happens? It becomes loose. So it becomes loose, it becomes detached. Now, when that happens, you see the slope of potential field of the ADP state. See here. The slope of the, you can say, incoming potential and the slope of the exiting potential is different. Now, let's not go too much into physics. The idea is that force is actually the gradient, it depends on the gradient of potential energy. So, the very fact that the slope is different means that there is a forward push. There is a forward push of the electrostatic force on this hydrolyzed kinesin feed plus ADP, which pushes it forward. So the complete cycle, the walking cycle results in this mechanism. So we have two apo feeds. Alright, now what happens here in the back feed? ATP attaches. Alright, now when ATP attaches, then it hydrolyzes to ADP. The moment ATP gets hydrolyzed to ADP, the feed leaves the protofilament. The moment it leaves the protofilament, there is an asymmetry in the forward and backward force because of which the ADP swung forward. It swings forward. Alright? And if you looked at this plot, you see the first binding site is 2 nanometer and the exact next binding site is 10 nanometer. So these are the most favorable positions, electrostatically speaking. So that is why the step size is exactly 8 nanometers. Alright, so as it swings, then again the ADP is lost and the apo feed goes forward, and then this previous feed again goes through the same cycle. Alright, so this is how the kinesin walking cycle can be explained, alright, using computational data in this case, using the Murban concept. So what all things have we been able to explain, alright, which were observed in the experiments? The 8 nanometer step conserved, the 8 nanometer step size, this has been explained very nicely because of the periodicity of the potential in the protofilament, that is in the microtubule surface. The directionality, it depends on the potential landscape of the ADP added kinesin motor domains. Also, there is no need for an engineered power stroke element. ATP to ADP hydrolysis does not cause the feed to jump from one point to the other. It merely detaches the feed. The motion is happening because of the electrostatic interaction. Alright, according to the Murban model. Alright, now one more thing which is very interesting here. Now the gliding part, what I mean to say is that this electrostatic force is a conservative force. What it means that if A exerts a force on B, B will exert a reaction force on A. What it means is that now, suppose hypothetically, if I hold this kinesin at its position, the protofilament should start to move backwards. Alright, which has been actually observed experimentally. Alright, sounds very weird, but it has been actually observed. And the symmetry of how it takes these steps is once again dependent on the potential landscape of the protofilament. As a matter of fact, it is these asymmetries because of which other proteins in the kinesin family, that is kinesin 5 and all, they are even able to move backwards. Alright, not just forward. So, alright, so now this approach explains the interactions of protein complexes, but it also opens an avenue in which how externally applied charged species and electrostatic fields can be potentially used to interact with biochemical systems, and potential applications can be explored. So such is the interaction of whole plasma. So this is a very engaging field which many biophysicists and biochemists are actually working on, and has got a lot of potential applications. So okay, so that, thank you.
Congratulations for very good work.
Thank you.
There are two aspects of the physics in moving, it's a quantum system. It's a quantum analysis system.
Yes.
and therefore there are lot of quantum mechanical calculations
Yes, sir.
necessary for that. And in one step, thermodynamics is a far clear system,
Yes, sir.
which was elaborated by Prigozhin,
Yes, sir.
and how chaos sets in
Yes.
in such a system. Therefore, what I feel is that this is a very beautiful concept, urban concept, which combines the Prigozhin chaotic system
Yes.
to Roger Penrose's quantum system,
Yes.
and therefore we may be able to come up with a new mathematical equations.
Yes.
For example, when we analyze that electrostatic potentials
Yes.
as it moves, and if we just calculate the information input done, with this simulate, predict, and concept, beautiful work. Congratulations.
Thank you. A very small scale, angstrom level scale, and a little bit larger if we go to micrometers or tenths of nanometer scale. So this model then definitely becomes something called a semi-classical model. So what sir is referring to, the Langevin equation, this is that equation that sir is referring to. And the exact diffusion D1, D2 terms that sir has asked to calculate, we have actually calculated, and they really seem to be fitted within the experimentally observed data. So it agrees with that semi-classical, part of which is quantum, part of which is classical model.
Years I've been working with collaborators and all that. It's the first time that I am not solving the problem. I suggested the problem, and a collaborator, I really don't know what's really happening. Now I have to sit with it. He took the problem, something like, I said the problem, I said these are the things. Would you take it? Would you do it? Do you want me to get into it? No. I'll take it. That's what he said. I still don't know what he has done, how he has done it. But then, this is the way I hope Mulburn goes forward, in the sense that I don't want to be solving everything. People should join in, people should take it forward. Because now I think with Mulburn, I'm coming to the end of, I want to get into social work. So I've solved enough number of problems. So if Professor Nampoori says that it's good, I trust him. And he said something to me yesterday about this work. I was so sleepy, I haven't slept for so many days. I will sit and listen to him more. Thank you. Yeah.
It's a beautiful book by Roger Penrose, Shadow of Mind. Shadow of Mind. There are all these descriptions are there. Quantum systems. Tubulin as a quantum system.
Actually, that was what I was also saying to the previous session. Actually, the quantum explains it better.
Yes.
Than the stochastic process. I'm a biologist. I don't know much about the physics. So that is now sir is also saying, because working with anesthesia with the Penrose model. Penrose model. Penrose, there is a model called the Penrose Hammer model for anesthesia. So that beautifully explains how the anesthetic is working.
Yes.
Really contrast of the current concept in anesthesiology.
So in that line, sir, actually this equation is a classical equation, functions and then we solve it. If I showed it, it becomes a little complicated. So I'll skip it in the analytic.
You can draw a nonlinear Schrodinger equation and solve it.
NLSE, yes sir. Thank you sir for mentioning.
Thank you for that nice presentation. It's not 100% stochastic model as
Yes.
Nampoori sir said.
Yes.
Because you have C alpha beta tubulin heterodimers
Yes.
repeating every alternate segment.
Yes sir.
And you see that your, I think the next slide or one of them, where there are so many interfaces, regularly coming.
Yes sir.
And see, you can see the
Yes.
blues and the reds.
Yes sir.
So it means that there is some determination,
Yes.
or there is no traffic is going on in that,
Yes.
in that direction. But how do you consider the entire thing as a one single unit? Say for example, you have a cargo sitting on top,
Yes sir.
and you have the cargo is bigger than,
Yes.
I always equate this
Yes.
to നമ്മുടെ നല്ല കുടിയുറുപ്പുകൾ വലിയ മാവിന്റെ ഇല പിടിച്ചോണ്ട് ഇങ്ങനെ
Yes sir.
So it's like that.
Yes.
So how does it so wonderfully does it? So the entire thing is working as a unit. So when it works as a unit, so our perception of, because we saw the beautiful video,
Yes.
where you only see part of the whole
Yes.
story.
Yes.
But surrounding that is where the urban is playing a big
Yes,
role. Where
yes.
all these electrostatic interactions and the oxidative reductive process,
Yes.
etc., is helping to maintain the whole thing so that the rest of the people can do its job for
Yes.
Correct. So that way it's very interesting. So you may have to do a little more of work
Yes.
along the line so that
So,
it can be
yes.
better or more better.
So the motion of the final step, that is the, see, so there are two things that I have done here. In this case, I have actually taken this head and I have dragged it along manually to see how it interacts with the potential. But this just gives me a hint of what is supposed to happen. The actual molecular dynamics run. This is done by solvating, so it's a 15 by 15. So there's a lot of water molecules also, and for neutralization we add 150 millimolar KCl solution. So, what you're saying is exactly correct, sir. So it's a big thermal bath. A lot of things are involved, and collectively this type of a pattern is coming. And the only reason this is very noisy, you get a lot of deviation, is because I pulled it rather quickly to finish it in the given time. But I'm still running it. The second thing is that protein, that cargo problem. What is known right now is if the cargo load exceeds the given value, it starts moving backwards. So according to these results, the hypothesis would be that something fluctuates in the potential landscape. But for that, now we have to start increasing the load. So that is the next part.
So that's the thing,
Yes,
the cargo load, if the potential force is enough to pull the cargo load.
That's what, sir. Yes.
ഒരു കാറിന്റെ കൊണ്ട് ലോറിക്ക് വെക്കുന്ന സാധനങ്ങൾ വെച്ച് കഴിഞ്ഞാൽ എങ്ങനെ കാർ പിടിച്ചു വിടത്തില്ല. So how do you bring that aspect into it? So you have to consider the entire thing as a one single unit, and there is a unidirectionality in here, and how these potential differences are playing a big role, in terms of, because some of the things what you showed is very interesting.
Yes.
And there the alpha beta tubulin retrodimer repeating aspect is coming in a big way.
Yes.
So it's a very organized system, but at the same time there's a lot of chaos in there.
Yes. So it's a deterministic but a stochastic system. Not deterministic, but the idea of the concept of Murban plays a role in the electrostatic landscape. It's a bigger picture overall, and definitely so that systems, that what you're saying, the cargo, considering the cargo as a process, it becomes a problem of the systems biology, which would be a much bigger computational work. But that is the next step.
That is one issue with the problem with the computational modeling work, because you can't recreate entirely cellular combinatorial complexity.
Yes.
Is there a parameter which you can control, or is only?
Yes, sir. So
parameter?
Yes, sir. That is there in each stage of the calculation. So if I start
parameter,
if I start from the beginning, so the Reynolds number, the diffusion constant, temperature.
There is one.
Yes, sir.
So by changing that control parameter,
Yes, sir.
then we may be able to come up with a bigger
Yes.
system.
Yes.
Bigger system.
Yes.
And ultimately goes to chaos.
Yes, sir.
Inside the chaos, there will be order.
Yes.
So life is said to be in order.
Only in a small scale. Yes.
It has emergent out of that.
Yes. Thank you, sir. Yes, sir.
I would like to make a comment.
Yes, sir.
Chemists are always interested in molecular motions.
Yes, sir.
Indeed, I think in 2016 or 17, Sauvage or Stoddard, etc., got a Nobel Prize for molecular machines. 2016 or 2009, I don't remember exactly. But what happens is that they thought about fulcrums, molecular motions, etc., based upon conformational changes.
Yes, sir.
Now, the interesting aspect I wanted to just think here is that in this we can perceive what you have shown as a video as a molecular motion.
Yes.
X moving on Y.
Yes.
Okay.
Yes.
So now what happens is that this molecular motion is not only simply X moving on Y, but here in reality there is a solvent system.
Yes, sir.
As well as there is big intermolecular interactions.
Yes.
The moment when molecules are moving,
Yes, sir.
they are interacting with each other.
Yes, sir.
So where does these two concepts. That is
Yes.
the solvent aspect
Yes.
plus the very weak intermolecular aspect taken care in your simulation
Yes.
or calculation.
Yes, sir.
This is the
Question.
the comment is our chemist's interest in molecular motion.
Yes.
The question is these two aspects.
Yes. So the answer is first, when I manually drag it, there I do not consider these things.
Okay.
But when I perform the steered molecular dynamics on GROMAX, it is engineered in such a way that it has to take all these effects, all the small to big forces, all the small to big interactions with it. The idea is, if this picture gives the same answer as the previous picture, then the small interactions that you have just discussed about are either too weak to be considered, or they are, as a matter of fact, enhancing the effects.
Okay.
So we see that here actually. So we see that exact periodicity of exact 8 nanometers occurring because of the combined effect, not just the electrostatics, but all the weak forces, van der Waals forces, everything that is present here. So the molecular dynamics, I don't have to solve any calculation. I have to give the system, solvate it with the all the water and everything that is there.
So the embedded algorithm will take care of it.
Yes, sir. Yes, sir. That's right.
But it is what is really profound is that the energy to push.
Yes, sir.
Okay, the petrol is the difference in the slope.
Exactly. Yes, sir.
In a formal way of saying,
Yes.
difference in the slope is the pushing.
Push, yes,
That's
sir.
very interesting.
Yes, sir.
Fantastic.
Thank you, sir.
ATP, energy involvement for the movement of this unidirectional process. So it's very interesting actually, because in diseases like Alzheimer's disease, many neurodegenerative disorders, all this is being affected. And there are so much evidence which we ourselves have created across the world. And the drugs are targeting these phosphorylation events, in which otherwise called as energizing events, that is taking place. So I think you guys should actively involve in on this process. It's a very interesting thing. In fact, some of the things can solve a lot of disease problems. Thank you. If there is no question, we'll go
I
to the
just
next
wanted to
one.
say something here. What's happening here? Yes, who's it?
Yes. Yes.
But I don't see how that's explained.
No, that I have removed that slide actually. But we saw that. Okay. So this was one aspect. This work extends beyond. So what I do is on the same protofilament, now I keep two heads, and I try to see how, using molecular dynamics, okay, I try to see how they're actually moving. And I also showed here that the feet, they are not just charged bodies. If you see here, they are dipoles. Dipoles means they will not just move in the electric field. They will move while rotating in the electric field. Alright, so that hand over hand swinging motion, no, that happens because of this dipole pattern. You see here, I will explain how is it. It's like a polarized molecule. Okay, so here you see this is a negative charge. This negative is blue. Just the color convention has kept it that way. Positive is red. Okay, so you see in the ATP state and the apo state, there is more differentiation of the red and blue. Alright, whereas it is not so much in the ADP. You can see the distribution is kind of, so it might not be very clear by looking at these plots, but when you actually calculate the dipole moments, you see a substantial difference. That is actually the reason why ADP is released.
So you're saying one might be ADP leg and one might be apo. Like one of the legs is
It is.
above and one of the legs is
No, I explained that here, the mechanism. Alright, so this mechanism itself dictates that the jump would be symmetric. Now the question is, in what case? The question is not whether it is symmetric or asymmetric. The question is in which scenario will it be symmetric, in which scenario will it be asymmetric.
Yes, I understand that. What my question was, so let's say apo leg and then you have ADP leg also, I think.
Yeah.
You go back to that slide. So you have two states over here, right? So there are two different three. So each of them have a separate distance which they can go. For example,
No.
so all of them have the same
No,
eight
I'll
nanometer.
explain. Okay. So the apo and ADP versions are very strongly interacting with the present potential, because of which they are very closely attached. The electrostatic pull between them is very, very nicely. Okay, think of a ball. Alright, now on the ball there is uniform distribution of positive and negative charges. Right? What is the total charge of the ball? 0. Right? But in the same ball, suppose on one hemisphere you have all the positive charges and in the other hemisphere you have all the negative charges. Total charge is still 0.
0.
But isn't that polarized now? Which means now if you keep that on the potential landscape, it will rotate. Do you understand?
Yes.
So that type of interaction is what is happening here. Alright, so in these two cases, there is strong interaction, whereas in this case, it is weaker interaction. Alright, so actually, Abhinav sir helped us last night with a lot of dancing to actually explain how this phenomena happens. We were discussing all this till I think 2 a.m. So what happens is when now suppose you have this apo. Apo means nothing is attached basically. Okay, that's why I use this term apo because the literature, the PDBITs use the term. So you have this feed in the apo state attached to the protofilament. Now ATP attached to it. So now if you look at the values of the energy, you realize in the black and the blue there is not much difference, right? Which means the structural strength or the gluing strength does not change when AP converts to ATP, T. But when ATP hydrolyzes to ADP, it becomes loose. Alright, see the energy difference is positive, which means now ADP state has more kinetic energy. More kinetic energy means it's free, like a free electron. Right? When that happens, it becomes loose. The moment it becomes loose, it will start experiencing this force. Even the ATP is experiencing the force, but because it is so nicely attached, it is not moving. But ADP is weakly attached, so it's pushing. That is what it is.
Thanks.
Yeah, I just want to say the thing, alright? So yeah, thank you. I think, thank you. Put your hands together. Summoned by the Institute Administration to Kollam. So I'm taking over because now we are